theorem. This is for the guy who introduces me. Everybody in this audience has to get one of these handouts. Okay? Just a single page, and everybody needs one. So, okay.
This would be a test.
They're just references. So this is a talk about applications of additive combinatorics, and it's joint work with Fernando Xiao and Soundarajan, in case I forget to say it. And it starts with a very primitive problem. When we add numbers, I don't know, 8, 3, 1, 0, 4, 1, 5. In the usual way, that's 11, that's 6, so there's no carry. I'll put a 0 there. This is 8, there's no carry. This is 5. Here, this is 0, there's a carry, and etc. Right? This is 0, there's a carry. This is 12, and there's a carry. When we add numbers in the usual way, carries occur along the top. Yeah? Yes, carries occur along the top. And if you're me or most of you, it's not an unnatural question to ask, how many carries are there and how do they go? You know, that's a question. And I won't say so much about it, but the process of carries, if the digits are chosen at random uniformly between 0 and b minus 1, base b, the process of carries is a Markov chain. And it has, and if you add m numbers, it's still a Markov chain, because if I tell you the carries process up to a point, what happened before doesn't matter, and just the future depends on the past only through the immediate past. And it's an interesting Markov chain with connections to all kinds of areas of mathematics, and it got me thinking about carries. So I want to talk about carries a little bit, and let's start with the carries matrix. So I'm going to take just adding 2 digits, say 0, 1, 2, up to 9, 0, 1, up to 9. Those are my 2 digits. If I add 0 to anything, I don't get a carry. 0, 0, 0. If I add 1, I only get a carry if I add it to 9, so I'll write a carry. I'll call it b, but b is 10 here. I get a carry if I add it to 9. If I add 2, I get a carry if I add it to 9 or 8. And if I add 9, well, b. So it's this part of the triangle, and there are b choose 2 carries. And so if you pick 2 numbers at random uniformly between 0 and b minus 1, the chance that you get a carry is this, which is 1/2 minus 1 over 2b. And that's equal to 45% if b is 10. So about half the time you get a carry. Okay. Now, the next stage, given that this turned out to be an interesting subject, I tried to think about what are carries after all. So that's a question. What are carries? Well, if you think that you have the group BZ contained in Z, for example, as 0 plus or minus b plus or minus 2b, etc. Plus or minus. This is a subgroup of this group. And then you choose coset representatives. And I'll choose the usual ones, 0, 1, up to b minus 1. That's, what else would you do? Then, unfortunately, the sum of 2 coset representatives isn't always a coset representative. So I plus j, well, is I plus j mod b, that's what it is, plus what's called a factor set Fij, which might be 0 or b. So in fact, carries, you get a carry if I plus j is bigger than or equal to b. This is b, and this is b, and equals 0. Otherwise, so carries are cocycles. So that was the title of the talk. Now, once you say that sentence, there are lots of directions open to you. One direction was, well, this is a subgroup of a group. I chose coset representatives, chose this one because everybody does. Is there a better choice of coset representatives? Can we do better? And by better, I mean fewer carries in some average sense. And my first reaction to that question was, can't be, because otherwise we'd know. Well, it turns out people did know. Cauchy knew. People before Cauchy knew. The answer is yes. I found it surprising anyway. What are called balanced coset representatives, namely 0, plus or minus 1, plus or minus 2, plus or minus b minus 1 over 2. Let me suppose b is odd for a moment. They do better. So just to point that out, let's do when b is 5. And so, okay. So my coset representatives would be minus 2, minus 1, 0, 1, and 2. Minus 2, minus 1, 0, 1, and 2. Okay, so here comes the quiz part of the talk. Okay, we have to fill out the carries matrix. So minus 2 and minus 2 is minus 4. That's true. Yeah. Okay, and minus 4 is minus 5 plus 1. So the carry, if you add minus 2 and minus 2, it's not a coset representative, is minus 5. And minus 5 here, and 0, 0, 0, 0, 0, 0, 0. If you add 0 to anything, you have no carry, 0, 0, 0, 0, 0. Here's 0, 0, 0, 0, 5. 1 and 2 are 3, which is 5 minus 2. Okay, and then 0, 0, 0, 5, 5. Okay. There are 6 carries. There are 6 carries. There they are. 6 is less than 5 choose 2. 6 carries. Less than 5 choose 2, which is 10. So balanced coset representatives do better. So you can ask now, once you make that leap, you can ask, well, can you do better? Why do you have to have any carries? Why? Okay. So an easy fact is that that's the best you can do. So in general, if you are base b, if b is odd, it's b squared minus 1 over 4 in general. And if b is 5, that's 24 over 4, which is 6. And so that's about half of b choose 2. And that's the best you can do, any choice of coset representatives. Is at least b squared over 4 and take the floor. If you're working, with an even base, say base 6, you would use 0 plus or minus 1 plus or minus 2, and then plus 3. Just put in one of them. Just make them neat that way. That's the best you can do. Carries. So this is a very easy argument, but let me do it, because the arguments get less easy as we go on. So proof of this fact this is a fact about real numbers. Say x1 up to xb. Let me put 0 in. are b minus 1 are distinct real numbers. Our coset representatives. You will have to have this many carries with, say, there are C positives. So let me call them 0, less than y1, less than y2, less than yc. Those are the positive numbers. If I add yc to anything, I get c carries. If I add yc minus 1, I get at least c minus 1 carries. Yeah? If I add y1, I get at least 1 carry, because I get a carry from that. Nope. Yeah? Okay. So yc gives c. Y1 gives 1 at least, and so this gives C choose 2 carries, forced on you by addition. Similarly, for the negative numbers, they induce carries, and well, it's b minus C choose 2 from the negatives. That's forced on you. And so altogether, whatever choice of numbers you have, so it's 1/2, whatever it is, C times C minus 1 plus B minus C times B minus C minus 1. And this, if you do it, is B squared minus 1 equals B squared minus 1 over 4, taking B to be odd, plus a square term, something that's positive, C minus B minus 1 over 2 squared. And that's bigger than or equal to B squared minus 4. So any choice of coset representatives has at least B squared over 4 carries. And that's sharp by these negative things. Okay, that gets us started in the question of how many carries do you have. This story makes sense for any kind of a group, this makes sense. The question makes sense for any G and H, and I'll take H to be a normal subgroup. I'll talk about that in a second. Suppose that H is a normal subgroup of a group G, and at the moment, let's suppose it has finite index. So this group G mod H is finite, like BZ in Z, wherever it is. So suppose you have a finite index normal subgroup of a general group. Let X be coset representatives. X coset representatives. You can ask, how many carries are forced, and how that goes. And most of those questions are open, but as a notion of how close X can be chosen to be a subgroup, so to have no extra carries, let C of X be equal to the number of pairs, ordered pairs XY in X cross X, such that X times Y is also contained in X. So that's the number of good things that can happen, and let me normalize it by to make it between 0 and 1. So if this is 1, it means for every pair X and Y, X times Y is in X, and so X is a group, and so we say the extension splits. If C of X is 1, X is a group, and so the extension is said to split. So a theorem that we proved after a while of honing it down is the following theorem, saying that, saying the following. So H is a normal subgroup of a group G with finite index. So if C of x, the number of good things, is close to 1, is bigger than 7/9, then the extension splits. And there exists a subgroup K, subgroup, such that K times H is G, and they only intersect trivially. K intersect H is the identity. So the extension splits. So, and this 7/9 is sharp, as you can see by 7/9 sharp from balance carries from C3, the integers mod 3 sitting inside the integers mod 9, and balance carries. Okay, that there are 2 carries if you choose balanced coset representatives. So this is an example of of a theorem, and I think it's worth. I think people in this audience, some people know certainly very well, but this proof went through many variations. Ben Green was around Stanford when Sound and I started on it, and we first proved it for the integers mod p inside the integers mod p squared using Balagour's similarity, and so we had a tower of 2s, and it was just some impossible theorem, nothing like 7/9. It was some impossible thing, and then it got better and better, and now it's this. Okay, so I want to talk about that for a minute, because the best proof came from computer science theorists, and it gives exactly the right answer. So the proof, the argument uses approximate homomorphisms. So the proof uses the notion of approximate homomorphisms. And I don't know the history of this subject, and one of the joys of being at a conference like this is you get to see your colleagues like Luca. And so Luca, someday I'm going to ask you this question, and be prepared. Well, this is just a warm-up. I'm setting it in the, which is, why do you guys use this? Okay, that's what's it about in the computer science theory world. But let me tell you what it is. So if you have 2 groups, G1 and G2 are 2 groups, and say G1 is finite, then, a mapping, say, T from G1 into G2 is an epsilon homomorphism if the probability that T of G1 G prime, these are both in G1, is equal to T of G times T of G prime. Probability means under the uniform distribution is bigger than epsilon. Okay, that's just the definition. So there's some chance that it behaves as a homomorphism. 2 elements picked at random in G1, that's true. There's a very nice theorem due to, see if I remember, Ben-Or, Coppersmith, Luby, and Ronit, Rubenfeld. which says that if you have an epsilon approximate homomorphism, so if T is epsilon approximate for epsilon bigger than 7/9, then there exists an actual homomorphism. There exists a homomorphism, say phi, from G1 into G2, such that the probability that they agree, T of G is equal to phi of G, so that is the proportion of elements in G1 such that these agree is bigger than or equal to some tau of epsilon. Where tau of epsilon is an explicit function, I hope, can people see if I write down there? Yes. So tau of epsilon is the smallest root of some quadratic polynomial, which maybe I remember, 3x minus 6x squared is equal to 1 minus epsilon. And since you can solve that equation, you know what tau of epsilon is. But in particular, for epsilon bigger than 7/9, tau of epsilon is bigger than 9/10. So tau of epsilon is bigger than 0.9, or 9/10. So this is a theorem that was proved in the world of testing if a random number generator is linear, or in testing program correctness, or that sort of thing. But it's a very nice theorem. And we were in the middle of our various variations of the theorem that I stated over there, and we saw 7/9, and we said this theorem must imply, we guessed that 7/9 was the right answer. This theorem must imply that 7/9 is, this theorem must imply that theorem. So I want to show you how this theorem implies that theorem. So proof of our 7/9 theorem. And so I need two groups. So what am I given? I'm given a normal subgroup of a finite index normal subgroup of a group G, and some choice of coset representatives, which behaves well 7/9 of the time. Okay, so let's let G1 be G mod H. That's a group. And G2 is equal to G. And let the mapping T of, well, these are cosets, GH, be just equal to X, where GH is equal to XH. So just pick the coset representative. That's an element of G, and that's a perfectly reasonable thing to do. That's our mapping. And if you look, the fact that the number of non-carries, the proportion of non-carries, is bigger than 7/9 says exactly that this is a, so this is a C of X approximate homomorphism. It's the same statement. So by their theorem, there is an actual homomorphism. So choose phi. And it's not their theorem. I mean, phi is reasonably explicit. It's reasonably explicit. Which is, from as above. Okay, choose an actual homomorphism. So phi is a homomorphism from G1 into G. Let K be its image. That's a subgroup equal the image phi of G1. That's a subgroup, and that's going to be our subgroup. From their conclusion is t and phi are equal, bigger than 9/10 of the time. So we know that since they're equal. So k intersect x, where they agree, is, well, let me do a very important inequality. Here, k is bigger than or equal to, well, k intersect x. Okay, that's certainly true. That's bigger than or equal to 9/10, the size of x, which is G mod k. So that's this 9/10, right? The chance that these two things agree is bigger than, and so the chance is pick something in G1 at random, and that's the size of G1. So we have that inequality going for us. And now, what is there to say? Well, let's see what there is to say. So it's also the case, I have a homomorphism. So by the first isomorphism theorem, this k is equal to, isomorphic to, G mod h, mod its kernel, mod the kernel of phi. Now, if the kernel isn't just the identity, its size is at least 2. And that's bad, right? The size of k, is now too small. So okay, 2 is bigger than 9/10. So anyway, this goes in the right way. So this inequality implies that the kernel of phi is just the identity, and so k is equal to the size of x. That's the first good piece of news. And if there's anything in the non-trivial in the intersection, if there exists some L which is not equal to 1, where L is contained in k and h, okay, then for any element in k, then any k in k, well, only one of k and kl can be an x. Right, because x is coset representatives, and so it can't contain two things that differ by a multiple of h. But that says that the intersection is at most half of the size of x. So that says that the intersection, if this were the case, the size of the intersection is less than or equal to the size of x over 2. And that contradicts this inequality too. So there is no such L, and so the extension splits. So since the size of h times k is equal to the size of h times the size of k divided by the size of the intersection, sorry, this should have been, this is fine. This is this. why am I want, no, I want that this is 1. No, that's okay. That's okay. So this size, this is trivial, and the extension splits. So it's a very straightforward argument from their 7/9 theorem to our 7/9 theorem. Sorry for us, but the truth will out. And oh, okay. So that gets us started. The paper that we wrote has a whole bunch of other theorems in it, and I want to tell you one of my favorites, and then I want to tell you some open questions, and then I'll stop. Okay, so you might have noticed that for the usual choice of coset representatives, for the, say, consider B, suppose B is odd, B, Z contained in Z. The usual choice of coset representatives, namely 0 up to B minus 1, there was only, the only kinds of carries you could have are nothing or B. The two carries, two types of carries. Namely 0 and B. For the balanced coset representatives, there were three kinds of carries. For balanced, we had 0, B and minus B. And, that's the truth. And a theorem is, if B is prime, theorem, if B is prime, and I'm working not here, but, and I'm working in CP, the integers mod P contained in the integers mod P squared, the carries table is the same. If I'm working in this setting, and if you can choose coset representatives, if we have X coset representatives for this subgroup in here, which have two kinds of carries, such that the carries matrix has two kinds of carries, A and B, 0 and B, whatever they happen to be, but there are only two different numbers that appear in that P by P matrix, then it's the usual choice of coset representatives, well, up to an affine change. Then there exists A contained in CP squared star, an invertible element mod P squared, and B contained in CP squared, such that X, such that if you translate AX plus B, that doesn't change anything. The carries, if X are coset representatives, then AX are coset representatives. Anyway, this doesn't change things in a bad way. That this is either equal to 0, 1 up to P minus 1, or 1 to up to P. One of the two. And so the usual choice of coset representatives is characterized by having only two kinds of carries up to a change. And the reason I decided to mention this theorem, first of all, I like it, and what's special about the usual choice of coset representatives? Well, this is one thing that's special about it, but it's the proof of this theorem uses the standard tools of arithmetic combinatorics. I won't prove anything, but why? Well, if X has two kinds of, if X gives two two types, if the carries matrix only has two types, then x plus x, then the size of x plus x is less than or equal to twice the size of x. X plus x is contained in the two translates of the set x, and so there's a classical theorem, Cauchy-Davenport, something like that, which says that I'll call it Cauchy-Davenport. It's always the case that for any set x of this type, x plus x is bigger than or equal to twice x minus 1. So if you only have two types of carries, the set, the size of the set is very severely constrained. And one of the main findings of arithmetic combinatorics is that if a set has this form, then it's very close to an arithmetic progression. And so using basic theorems of Freiman, we're able to, we had to change them because we were working mod p squared, so there was a little something to do, but it wasn't so bad. And this theorem it uses the basic tools of arithmetic combinatorics. Some version, just in case you want something to think about, some version of this is true. It doesn't have much to do with primes, but we can't touch that. We couldn't touch that for more general things. So the last two things I want to do, I want to make a comment and pose one of many problems. The paper is full of both comments and problems, so if you're interested, I hope you take a look. Let me first make a comment. You can ask this carries problem, why normal? I mean, given a subgroup of a group, it makes sense to choose coset representatives. It doesn't have to be normal. So for a while, we thought the theorem was true more generally. Do we need H normal in G? And Marty Isaacs and Bob Guralnick found lots of counterexamples. I'll just tell you one, but still, there's probably something to understand. So I'll, yes. So here's an example, a family of examples. So there, if Q is 2 to the n, where n is odd, bigger than or equal to 3, there's a group called the Suzuki group of Q is one of the finite simple groups. Are very closely related to such, is a group of order, see if I remember, q squared times q minus 1 times q squared plus 1, basically q to the 5th. It's a group of that order. There is a subgroup of this size. There exists H, which is the Borel subgroup, size of H is equal to q squared plus 1. But there is no subgroup of size, there's no complement of it, no complement. Okay, so the extension doesn't split. But the CeLO 2 subgroup, there exists, let me call it K1, size of K1, that's the CeLO 2 subgroup, is q squared. And so this is two group, this is definitely not, and so the intersection between these two groups is trivial. And the product is almost everything, but there's a little extra, since K1 times K1 or can be chosen as coset representatives, but you need one more, K1 and one more, any one, and one more X give X coset representatives for H in this Suzuki group. And how about the carries? Well, since K1 is a group, the product of all of those things is always still a coset representative. So C of X is bigger than or equal to, you might have, but it's the size of K1 squared. So I'll just write, well, I'll write the size of K1 squared divided by the size of X squared. X is Q squared plus 1.
Persi, what is X?
X is the CeLO2 subgroup and one other element. Take the CeLO2 subgroup and then complete it to coset representatives by adding one further. X has to, you have to choose a coset representative. No?
I just try. It seems that X has been used in a few different ways.
Well, sorry, there's a little, okay. This is a little x. So capital X is K1 union the singleton element X. Okay, that is K1, those are giving distinct, the translates of H by K1 are all distinct, and then you need one more coset representative to complete things. And this ratio is very close to 1, right?
What do you mean by X is a set of coset representatives for H?
For H in G. H is a subgroup, right? H is a subgroup, and K, the translates of H by K are all disjoint.
Right, but they don't cover
But no, they don't, so you need one more. If you count.
But they still don't, because we only have like Q squared plus 1 squared.
Four, yeah.
You only have to like the 4 elements.
No, I don't. I don't. I think I only need one more. I think I only need one more coset representative. That is, this gives me this many, and falling off. That was a tough question, Terry. Okay, so it might. Well, let's see. I thought I only needed one more. Let's see. So each. That's. Okay, so far I have that many elements, right? Right, and then, okay, so I need to get, so maybe I have to choose Q minus, it'll still be okay. I need to choose, I thought I only needed to choose one, but.
K needs to have size about Q
cubed. Right, it's true. Okay, so you're right. Q minus 1. Okay. It won't cause trouble. Okay. It won't. I hope we can calculate now. Okay. No, I don't think so. That is a full choice. The number of coset representatives I need. It's true. I see.
So maybe the Borel set has size Q squared times Q plus Q minus 1.
No, but it has to have no true torsion. It can't have a Q squared in it.
Okay, so I'm confused, but thank you. That's fine. I don't mind. I'm doing disservice to honorable group theorists who did a careful argument that I'm just not remembering correctly. But if you do this properly, you do indeed get C of X bigger than or equal to 1 minus epsilon, and so that is a claim, and I haven't established it, and I won't pretend to, but I will in 1 second. I mean, not in real time, probably. This argument is quite general. If you take any finite simple group and take its Borel, Lie type, and take its Borel subgroup and take the opposite, but with ones on the diagonal, then you can complete that and And there are lots of counterexamples. So done correctly, this is bigger than or equal to 1 minus some, 1 over q to some power, and yet the extension doesn't split. So okay, sorry for saying that incorrectly. Let me take one more minute and say an open problem that we would love it if somebody would solve, but I'm sorry for messing that up. And that's, we have a 7/9 theorem. So given H a normal subgroup of G, say a finite index, let's let C of HG be the maximum it can be the maximum over all choices of X. So we showed that in some examples this is if the extension doesn't split, there's a 7/9, but for the integers mod b inside the integers mod b squared, this can be 3/4. So and the question is just to determine what this maximum is. For example, what's the best? How large can we make is C mod B Z? Just take 2 copies, BZ in B cross C. And we conjecture that it's 9/16, which is 3/4 squared, plus little o1, and B is large. But we can't prove that. And so the paper is full of simple questions like that probably have reasonable answers. And Fernando Xiao has a paper going somewhere towards this, but not quite there on the archive. And this particular question is, what's the best choice of coset representatives for this subgroup in here is still open. And then you could take any group and any subgroup and fiddle around. Okay, so that was a look at the subject of carries and cocycles, and it is the case that it makes very heavy use of the tools of arithmetic combinatorics and of these nice results about theoretical computer science. So I'm impressed. Thank you.
Questions?
Or a patch of this argument. Yes.
So if you take something like H to be a product of loads of copies of C2 and G to be a product of loads of copies of C4, it's presumably really hard to get an efficient system of carries in such a setting.
Yes, that's right. And so then I repeat the question. If you take take G to be a bunch of C4s, integers mod 4, and H to be a bunch of C2s, that extension doesn't split, because C2 inside of C4 doesn't split. And what's a good way of choosing coset representatives? It reminds me of a very parallel question, and it's close, but the theorem that we proved is so general. I mean, any group in any finite index normal subgroup, there must be some infinite version of it. I mean, there must be some version for non-finite index subgroups. So we can prove that if you have a compact group and a closed subgroup where the quotient has finite Haar measure, then if you pick 2 coset representatives at random, and if the chance that there's still a coset representative is bigger than 7/9, then the extension splits. So we have a continuous version, if you like, but there must be, we're not afraid of dealing with infinite things. We can take limits. And so I thought, well, take a whole bunch of C4s and a whole bunch of C2s, and then I wanted an example of an infinite index subgroup where the extension doesn't split, but I don't have any progress to say. And you were asking a nice finite question, which I don't.
I mean, do you think that's somehow the worst example?
Sounds kind of extremal, doesn't it? I mean, C2 and
What's the
C4.
example? What's-
You know, where it would be hard to make an intelligent choice of, yeah. We didn't think about it. I think it's fair to, we kept reading your Barbados notes and discovering more things in them. So that's what we were spending our time doing. No, okay. But if you haven't done it, that's one thing to learn. Look at Ben's Barbados notes. They're full of useful stuff.
I guess the constant 7/9 cannot be improved under any reasonable assumptions.
I don't know. That's what this is sort of asking about. You know, if you have specific example, you seem to be able to improve 7/9, but and what's the best you can do? What's the best choice of coset representatives in specific examples? That was what I meant to have the flavor. But you're asking maybe for a general theorem, you know.
Well, I guess the counterexample is already disappointingly simple. Like it was Z3 is Z9.
Inside of Z9, but still, okay, I don't know. I don't.
But there should be an inverse theorem. That if C is bigger than any epsilon, then there's some bound complexity of how close you are to splitting, which depends only on epsilon. So that's the usual experience of that. So by the way, this example can be fixed. It's just that the Q sub plus 1 is not the order of the Borel, it's the index of the Borel.
Ah, yeah, that's right. Thank you. That's right. And I wrote down and crossed it out twice in my notes, but I left my glasses home, so I can't read my notes. But thank you. I have you. Thanks. Right. Q squared plus 1 is the index of the Borel. That's right. And then it is. You just have to add 1, and it's okay. Bad to completely screw up Marty Isaacs. Nice example, but thank you. Okay.
No, that's right.
That's it.